And lastly today, we're coming back to do a bit more of this question. We've done the first bit before, but there's a real twist at the end. Okay, so first of all, it's calculating the speed again because we're going to need it for the last bit. So there's the frequency, there's one wave, so wavelength is 60 centimetres. And so once again, put your numbers in, and that gives us 72 metres per second. Okay, and then we're told that this speed is equal to a constant times the square root of W, where W is the tension in the string. So that's going to be equal to the weight of the masses there. Okay, so we're told that for what we've just calculated, the weight on the end of the string was 4. And so we've got our 72 metres per second equals K times the square root of 4. And so K is going to come out as 36. And then for the last part, we're told that the frequency is going to stay at 120 hertz. So we still know F, but then we're asked, are we still going to get a stationary wave when W changes to 9? Okay, well, we know what K is now. So first of all, we can work out if we've got a new W, we're going to have a new V. So putting in K is 36, the square root of 9 this time, should have had 2 sig fig there, and so that's a new speed of 108 metres per second for that wave. But if we've changed the speed and frequency has not changed, that means we're going to have a new wavelength as well. So putting our numbers in there to get the new wavelength, we're going to get 0.9 metres. So if we've changed the speed, haven't changed F, we've got a new wavelength. And the very last part of this question is asking, okay, so we've got a new wavelength, 0.9 metres. Is that going to give us a stationary wave? And the answer is yes. If the wave is 0.9 metres, well, that's this distance. So we're going to get exactly one wave in that space there. So yes, we will still have a stationary wave. Well done if you got all the way through that and got only 3 marks. I mean,